This is the screencast for section 7.3, example 2, a solid of revolution. Now, what that means is we're actually going to be taking the area under a curve, or sometimes in between two curves, depending. Right now, just area under a curve, and we're going to take that and rotate it or revolve it around the x-axis. So what that means is if I have this area, this time it's between two curves, no big deal, I'm going to, now watch over here, rotate it around the x-axis to create a solid object. Now this solid object has a hole in the middle, and we'll talk about that in later examples. It's not being revolved around the x-axis per se. We'll also talk about that in later examples. But for right now, the idea here is we're going to be taking the area of a curve and revolving it around. Now, that's how we get the picture of our object. We're still thinking of this as a sliced object. But this time, all of the slices are going to be circles because it was revolved around the x-axis. So you can kind of see here the region between the graph of f of x equals 2 plus x cosine x. So that's the graph up top, f of x 2 plus cosine of x. The area under that, stretching between -2 to 2, is revolved about the x-axis to generate a solid. So you can kind of see this pink circle in here that represents one of the cross sections. We're going to try and find the volume of this solid. Well, since this was rotated around, it's a circular shape. So here we are with our circular cross section that we can look for the radius at. Well, I can see that the radius of my circle here stretches from the x-axis up to f of x. So the radius is actually going to be the f of x curve, or y. So on my drawing here, the f of x curve would be kind of at the top of each circle. No matter where the circle is on the x-axis, f of x is up there. So the radius is always going to be 2 plus x cosine of x, the height. So if it was out at 1, it would be 2 plus 1 cosine of 1. If it was at -1.5, it'd be 2 plus -1.5 cosine of -1.5. So the cross section is going to be a circle, and its area is pi r squared. So in this case, it's pi, and then the radius we said was 2 plus x cosine of x squared. So each radius is the distance from the x-axis to the curve. So now the volume, we're going to add up all these circular cross sections from -2 to 2. They all have the area pi r squared, where their radius is 2 plus x cosine of x, and we're going to give them a little bit of thickness with some dx, so we create a volume. I did the antiderivative in my calculator, and I get 52.429 cubic units. The now try problem number 7 says find the volume of the solid generated by revolving the shaded region about the given axis. So we're going to revolve this about the x-axis. This shaded region is a triangle. If we revolve it about the x-axis, this whole triangle gets revolved. You may picture this, it's going to look like a cone. Each cross section is going to be a circle because we're revolving it around, we're spinning it. And as you can see, the radius is again just the height of the curve here, no matter where we are in our cross sections along this cone on the x-axis. So the cross section is a circle whose area is pi r squared. Now we just need to identify what r is. Well, r is our function, the height, the y value, which is going to be, x plus 2y equals 2. So we got to solve that for y. So I get 1 minus 1/2 x. So now the area is going to be pi times radius squared, where the radius is 1 minus 1/2 x. So the volume is going to be all these cross sections stacked between 0 and 2 on the x-axis. Now I put the pi on the outside for the area of the cross section, so pi and then r squared. Give them a little bit of thickness so we create some volume here, and that is for the dx. Now I will multiply all that out so it's a little bit easier to integrate. And then I'll integrate fundamental theorem part 2, and I get 2.094 cubic units. I checked it on my calculator just to make sure, and really to find that final answer. Yuck.